Many complex systems characteristically display a loss of complexity in their output as they decay or become ill. This is often one of the earliest signs of disease and may be used as an early and sensitive diagnostic clue. However, there is not a single universally accepted method of measuring complexity, and even the proper term of complexity is sometimes open to debate. In the field of diabetology, one of the most frequently used metrics is the trend fluctuation analysis, or DFA. The present tutorial tries to give clinicians an intuitive idea of what does DFA measure and what does it mean. The main idea lying behind DFA is to assess how the informational content of a time series is distributed. We will try to explore this idea through the map versus territory metaphor, first in the space domain and then in the time domain. One could argue that the more complex the territory, the more its description will depend on the small details. This means that the informational content will quickly degrade as the scale of the map decreases or as the graining of the image becomes coarser. Instead, a less complex structure will retain more significant information well into larger scales. Consider two pictures. As the pixel size increases, details are quickly lost in picture B, while picture A retains much of its meaning well into larger pixels. Arguably, picture B is more complex because it depends more on the small details. A similar reasoning can be applied to a time series. This is exemplified in the next slides. In this case, the territory is the time series and the map's pixel would be a linear regression of a certain number of consecutive points. As the number of points in each window increases, this is pixeling by enlarging the time window, the fitness of these regressions deteriorates and the gap between the map and the territory, this is the gray area, increases, just as what happens when the graining of a picture becomes coarser. Inversely, if one starts on the biggest window, this is the whole time series, and one represents it with a single linear regression, the territory to the map gap is large. As the time window decreases and the number of segments increase, the map, this is the set of lines, tends to stick to the territory, so the quality of the picture increases and the gap is reduced. The more complex the time series, the more it will depend on the small windows. Conversely, a less complex time series will still retain a significant amount of information encoded in the large windows, and therefore will still be increasing its map to territory gap well into larger time windows. Note that the important aspect is not the size of the gap, but the rate at which it grows as the time window enlarges. Complex time series will enlarge this gap slower than non-complex series. This is all that lies behind DFA. How do we calculate DFA? The first step is to measure the map to territory gap for each time window size. Formally, this is done through this equation, where Fn is the gap for a certain window size, n is the number of points in the time series, yk is the value of the time series at time k, and ynk is the value of the regression point at time k. If the time series has a fractal structure, and glucose time series do, there will be an exponential correlation between the map to territory gap and the size of the time window, and therefore a linear correlation between the logarithm of the gap and the logarithm of the time window. DFA is precisely the slope of this linear regression. In the next slides, we see how the map to territory gap evolves as the time window increases in two different glucose time series. The graphic on the right displays the correlation between the logarithm of the gap and the logarithm of the window. If we compare the rate at which the map to territory gap increases with the time window in this time series, it is apparent that the complex series in the lower window has more of its relevant information codified in the small time windows, and therefore the rate of increase in the gap is smaller. This is displayed as a smaller DFA. Remark that generally, before submitting the time series to the windowing process, the time series is pre-processed through integration. This has certain advantages. Most notably, the resulting set may be interpreted within the framework of a random walk model, which gives some important clues on the biological meaning of certain values. However, pre-processing through integration flattens the time series, arguably erasing important clinical information. Therefore, we tend to omit this pre-processing. Recapitulating, DFA measures how the correlation between successive readings of a time series evolves depending on the length of the strand considered. However, most biological systems are subject to a homeostatic control mechanisms that tend to correct and revert any long-lasting trend. Therefore, inevitably, as the length of the time window increases, the correlation will degrade. A brisk, healthy physiological system will soon detect and correct minor deviations, and therefore the correlation between successive points will soon decay. Instead, a harmed system will be slow in detecting and correcting trends, and therefore successive readings will retain a better correlation well into larger time windows. Therefore, DFA is lower, this is high complexity, in healthy systems, and increases gradually, this is lower complexity, as the system becomes old or diseased.